1. Section 3.9, derivatives of logarithmic and exponential functions. And this one you'll also have a logarithmic differentiation. I named this on YouTube as logarithmic differentiation because that would be the highlight of the whole procedure. And we'll see why and how is that helpful. We're going to start first with a few of those basic definitions. Well, those are theorems, results. And then we'll upgrade. So the first thing is we know that the derivative of e to the x is e to the x. And then if you guys use the chain rule, what happened? If you have a function in the exponent, it's going to be e to the f of x times the derivative of the function because that's the chain rule. The only thing that we want to take a look at now is what happens if you have any base. So if it's not only e, but any base, what happens if it's 2? What happens if it's a half or a 1/3 or 7? Well, in that case, we get to multiply all of this by ln of a base. So it's going to start with ln a, and then times a to the f of x times f prime of x. Now, this formula here is the most general case for exponential functions. All of the formulas above are special cases, and you can see that because if a is e, it reduces to the second equation. If a is e, then ln of e is 1, and then you have e to the f of x and then times f prime. And if f of x is x, you can see that it reduces to the first equation because, again, you would have e to the x, and then f prime of x, which is derivative of x is 1, so you just have e to the x. So in some sense, that formula down there is the most general case. Now, we don't have too many applications out there that would use this, right? Because you rarely see 2 to the x or 10 to the x or quarks. But e to the x is featured almost everywhere. So we really want to know the first and the second, and we want to know that the third one exists. Now, obviously, it will show up on a test. You should know it, but then most likely that will evaporate. And, you know, it doesn't show up in Calc 2, Calc 3. It might show up maybe once or twice in differential equations. But, you know, it's not a result that you have to use on a regular basis, and something that you can review and, you know, look up the reference and so on. But you need to know it now. That's the first part. The second part are the formulas that involve derivatives of ln, which are the inverses of exponentials. So we start again with the most basic case, with the ln x, whose derivative is 1 over x. And then we are going to spice it up a little bit. So we're going to have ln of f of x. So if any function, sine x could be ln of anything. In this case, you write the function as is in the denominator and its derivative on top as a chain rule. So that would be that, and then obviously we are going to have again the derivative of the logarithm with any base. Derivative of log of any base. So again, that's going to be the most general case. So log of base a of f of x is going to be, again, ln a times f of x in the denominator and then f prime in the numerator. And that would be the most general case for logs. Actually, it's a terrible box because it cuts through derivative. So now let's just do a few quick examples of this, because this stuff is, as I said, basic, so that we can get into logarithmic differentiation, which is the hefty part of this thing. So what is the derivative of, let's say, ln of sine x? Well, take the argument, which is sine x, Control C, Control V, into denominator. And what's the derivative of sine x? Cosine x. So all together becomes cotangent x. So derivative of sine x, ln of sine x is cotangent x. Awesome. What is the derivative of, I don't know, ln of x times x? What happened? Yeah, anyone? Do what? 1 over e to the x. Why? They would say you took a stab at it. So, who remembers the properties of logs from pre-calculus course? You do? So what's the ln of a product? No? Nice! Yep, adding. So, we can actually cheat here a little bit. We don't have to. There's a product rule in ln, so you can go and write x times e to the x in denominator and then do the product rule on top and then simplify. But we can also do this, where this guy is just x. Awesome, right? So what's the derivative? 1 over x plus 1. That's the derivative. Now you must get the same answer if you actually force the formula with the product rule and then solved it. So the denominator would be x times e to the x, and then the numerator would be copy the first one derivative of the second plus copy the second derivative of the first. And now when you simplify that, you pull out x, and then you have x plus 1 divided by x, and then you pull e to the x, they cancel, and now when you divide, you get 1 plus 1 over x, as you can see. So yeah, it can be done that way, but it's much easier to know the properties of log from pre-calculus, as I'm noticing that some of you are drifting away right now. Afraid of logs, are we? No? Yes? Or they're heavy. A log is very heavy. That's why the books are so heavy. Anyone caught the two-way reference there? Use trees to make books, right? But then logs are in books as mathematical concepts. It's heavy either way. Anyway, let's have a little break from this to talk about the logs, so we're not freaking out too much about logs. Because what is coming up right now is logarithmic differentiation, and that's going to be used later on. And logarithmic functions need to be well understood in order for the rest of the math to happen for you guys. So let's talk briefly about that. In order for me to have 30 minutes, so this is going to take less than less than 2-3 minutes. So 3 plus 2 is very good. And then 5 minus 2 is, and 5 minus 3 is. So if you take a look at this calculation, I have addition of two numbers, and then I am able to retrieve both of those input numbers by using the opposite operation from plus. Then I have 3 times 2, or 2 times 3 is 6, and then 6 divided by 2 is, and then 6 divided by 3 is, and as you can see, the same thing happens. I have the operation, and then if I use the opposite operation, I'm able to retrieve both of the input factors. So we have addition, we have multiplication, which is fast addition, and now we have the fast multiplication, which is repeated multiplication, which is exponents. In some sense, that's the uber fast addition. So we have 2 cubed. And if I write 2 cubed equals to 8, because 2 times 2 is 4 times 2 is 8, we have 2 cubed is equal to 8. Now, what's a cube root of 8? 2. Awesome. How do I retrieve 3? How do I retrieve 3?
Log.
Yes. Log. Log base 2 of 8 is 3. And that's where it falls in the world of math. If you are looking at this progression over here from addition all the way into exponents, log is the inverse, as well as the radicals are inverse of exponents. You have to understand that log is mathematical operation like addition or subtraction. Now the reason why most of the people are discriminating against it, unrightfully and unjustly, is because it doesn't have a cute symbol for it. It has letters for it. L-O-G. And, you know, you've been doing this for 15 years, and you've been doing this for 15 days, and then obviously that's going to be the outcast, right? But you have to understand it that this is as good as that, because it's going to spit out 3 by providing the 2 input numbers. It combines numbers in a different way than these operations. Each operation is unique in its own doing. So log is one of the operations. I understand that it would be much easier and nicer if we had some kind of different notation that did not include numbers. Probably would be less threatening and less intimidating. I don't know, whatever. Put AR2 and then there you go, you get 3. Perfect, right? So if you had some kind of different symbol for it, maybe it would be better understood. You have to understand that this is operation, just like addition or division or whatever else, and log on its own is not a function. Just like this is not a function. It's a calculation. It's part of arithmetic, just computing numbers without any hint on graphing, domains, anything like that. When does this become a function? It becomes a function when you replace one of these with x, right? And then you say output y will be x plus 2, and then you can go and, you know, and do this. Same thing happens in any of these cases here. You go and you replace one of these with the value, so let's say 2x, so y equals 2x. Y equals 2x, again, is going to give you some kind of function. So as soon as x creeps in and you have a variable, then these expressions here become functions. So now log 2 of x becomes a function, and its graph, and all of the other things. So regard the log for what it is. It is the operation that takes 2 numbers and combines them in a particular way to get the third number, just like any other operation out there. If you put x in it, it becomes a function, and then we have domain and range and everything else that every other one of these will do the same if you put x's around. I hope that eases a little bit on logs. Now, knowing that, we have the difference between log and ln? Well, it's just a lazy notation because log with base e, where the e is that natural log base, is everywhere. Everywhere. Doesn't matter whether we're talking about science or we're talking about, we'll see some examples eventually in this class as well. Whether we're talking about the finance or biology population or carbon data, archaeology and history, or you're talking about electrical engineering to charge and discharge capacitors for electronics, or you're talking about nuclear physics for rates of decay. You're talking about the medical field on metabolizing a drug in bloodstream, talking about the half-life of matter and drugs and everything else. It's in every aspect of human endeavor, everywhere, that e to the x. And because e to the x is so special, then writing log base e, log base e, log base e, let's just do ln. It implies log base e. So there are a few things that we have to understand about logs. So let's start, just going to summarize all of this now real quick. So log base 2 of 8 is equal to 3, and we understand from there that it's just a calculation, maybe just like as saying 2 plus 3 is equal to 5, where, you know, 2 plus 3 plus is this cute symbol that we are used to, and log we're not. Next thing is we are understanding that the log of x is equal to log base 10 of x. So if there is no base, the base is 10. You're going to see this in physics and chemistry. Chemistry has it for calculating pH values. Physics has it for, let's say, sound intensity or decibel scale and so on, the earthquakes. So base 10. But the most widely used one is the base e. So when you see ln x, that means log base e of x. And again, all of that feeds back into just calculating numbers. The function for it is y equals log any base of x, whose graph looks like this. It has the vertical asymptote at x equals 0. It goes through 1. Domain is 0 to positive infinity. Range is from negative infinity to positive infinity. So all of that stuff you can read from the graph. Now, what we want to know here, what we want to know is the properties of logs. So properties are, and I'll write them as ln's because less letters than writing log. It holds for every base, not just e, but we'll write with e. So ln of xy is ln x plus ln y. Ln of x over y is ln x minus ln y.
Sorry to interrupt, but there's two questions. Does our lab need to have a summary?
What happened?
Does our lab need to have a summary?
Yes.
It does?
Seriously?
Yep.
Like a paragraph?
Paragraph. It's good.
Sorry to interrupt. Have fun.
And the last one is the power of the argument goes in front as the multiplication. So, and I'm going to box this. I don't know if you're sensing the tone, but the tone is definitely there. All right, how about now? Better? Good. All right. So that was a quick review of log stuff from the past life. Now let's go and take a look at logarithmic differentiation. The book did wonderfully disgusting job at it, so we'll have to invest maybe time at next class as well tomorrow to do more examples and understand it better. Let's take a look at a function. Let's say y equals to something cute, like cube root of x squared plus 1 times x to the 5th power minus 3x minus 10 to the 8th power divided by x plus 1 to the 4th. Looks good? So what would be the derivative of this? Anyone? What would be the derivative of this function? Or at least what are the rules that are involved to solve this? What's the main one, let's say? Quotient rule. Excellent.
You put it in ln, and then the log rules to separate it into.
Yeah, but that's the logarithmic differentiation. I'm talking about the regular way of solving.
Oh.
So what do we have? We have a quotient rule, right? You have a quotient rule, and then you have a product rule, and then you have a various chain rules along the line, because each one of these is its own chain rule. So every time you have to take the derivatives, there will be chain rules all over the place. Now, what if I told you that with intensive 2-day training, you would be able to take a derivative of this mentally and write it in a factored form without any work? And just imagine being able to do that with this, meaning that every previous derivative we ever learned in this class would be far more trivial than doing this. I've been doing this for a long time, so I can just look at this and dictate the answer. And I can tell you that with investing the right amount of time, every one of you should be able to do the same. Now, wouldn't you like to know how to do that? Yeah, well, if the time permits, right, and if you're sufficiently interested, you might be able to learn that. And it's going to be exactly what was said before. The trick is to apply ln on both sides and use those 3 rules to disassemble this into a very, very basic derivatives, which is ln of f of x. So if you can just keep track of that in your head, the rest is a joke. So what's the derivative of this thing like that? It's going to be, I'm just telling you the answer right now, and then we're going to see how it's done. So the derivative of all of this mess is very simple. This thing as is times, open parenthesis, and we're going to start here. 1/3 times 2x over x squared plus 1 plus 8, and then you have the 5x to the 4th minus 3 divided by x to the 5 minus 3x minus 10 minus 4 1 over x plus 1, close parenthesis. And that is the factored form, the derivative in the factored form of this problem. Now, something that should take about 30 minutes doing by hand if you're going a chain rule, quotient rule, and all of these things to keep track. So it is possible for you to learn to take this derivative mentally and just write immediately the answer, meaning that every previous derivative we did in this class from day 1 till today would be far easier, far much faster than this without any rules. You can completely forget about the product rules and chain rules and everything else just by learning how to do this one thing. But again, it needs to be intensive training for some time for you to pull that off. Now, I'm going to leave this example just for a tag. I'm going to explain the procedure on a simpler example, and then we're going to go back and do this one as well. So let's start by looking at y equals, we're going to leave some space here, and let's go with something much easier. So let's still do cube root of, let's go x plus 1, and then maybe have over here x squared plus 2, and then over here, let's leave x, let's just go x to the 4 because we can. So let's say this is the problem. Less writing and less congested than the previous one. So the trick is to take ln of both sides and then disassemble the right-hand side completely using the three rules where I said, do you sense the tone? So if you're able to do that part mentally, the rest of the problem should be quick. So I have ln y is equal to, and now I have anything that is in the numerator is going to be plus ln, and anything that's in denominator is going to be minus ln. So we have ln of cube root of x plus 1 plus, because the second one is in the numerator as well, ln of x squared plus 2, and then minus ln of x to the 4. So what I've used here are the rules 1 and 2, where I am breaking products and quotients into additions and subtractions of logs. And now I'm going to use the third rule, which peels off the exponents. So ln y is equal to 1/3 ln of x plus 1 plus, there is nothing to peel over here, so just copy that one, and then minus 4 ln x. The next step is to differentiate, because notice that each one of these is ln of f of x. And what's easier than just copying the function in denominator and putting its derivative on top for basic functions? Nothing. Nothing easier than that. So it is at this time where we differentiate everywhere, and note the implicit differentiation on the left. Derivative of ln y is 1 over y dy dx. And then we have the rest. So now, the derivative, we copy 1/3. Derivative of ln x plus 1, Control C, Control V. You put x plus 1 in denominator, its derivative on top. Plus, copy the function as is, its derivative on top. Minus 4, copy the function as is on the bottom, its derivative on top. The derivative that we are using is that derivative of ln of some function is that function as is and the derivative on top. That's what we used everywhere. Derivative, see x plus 1, copy it down. Derivative of x is 1, derivative of plus 1 is 0. Move to the next one. X squared plus 2, copy it in the bottom. Derivative of x squared is 2x. Copy x on the bottom. Derivative of x is 1. So now, the only thing that you need to do is to move y to the other side and leave dy dx alone, and then you plug in what y is. So dy dx is equal to y times, and then you have the open parenthesis, 1 over 3x plus 1 in parentheses, plus 2x over x squared plus 2, minus 4 over x. And you just plug in the y. This is your y. So you just plug that down there, and you're done. So dy dx is equal to, now what was y? It was cube root x plus 1 times x squared plus 2 divided by x to the 4th times 1 over 3x plus 1 plus 2x over x squared plus 2 minus 4 over x, and that is the derivative. And I am claiming that you can do this mentally directly. Just read this off of the equation. The derivative of this here is always going to be itself times, and then you just focus on each one of these separately. Get out of here. So now we are going to go back to our more involved problem and use the same method again. Y is equal to, it was cube root of something more involved, if I remember. Oh, I know what I'm going to do. There we go. So now let's solve this problem together. What's the derivative? The derivative must be the problem as is, which is 3 square root of x squared plus 1 times x to the 5 minus 3x minus 10 to the 8 divided by x plus 1 to the 4th times. And now we start. The first thing what we do is we notice that the exponent is 1/3. That would go in front of the ln. And then ln will take the function as is on the bottom and its derivative on top. The next term is times, so it's plus, it's in the numerator. You have the exponent is 8, so times 8. Copy the function as is on the bottom, which is x to the 5 minus 3x minus 10, and put its derivative on top, which is 5x to the 4th minus 3. And the last function is in denominator, which means minus. There is the exponent is 4, so 4 times, and the function goes as is on the bottom, and its derivative on top. And this is the derivative of the whole thing, without doing any work. You are keeping track that all of the terms that are in the numerator are going to be positive, and all of the exponents that appear are going to be the coefficients in front, because ln peels those off. And then all of the denominators are going to be subtracted. So you can have multiple terms in denominator, obviously. All of those will be subtracted with constants multiplying them. So when you have square root, cube root, fourth root, and so on, the exponents are a half, a third, or something. So you see that the cube root spawned 1/3 as the coefficient. And number 8 and 4 spawned 8 and 4. So you just have to be careful about that. Whatever is inside the parentheses or under the root or so on, that's the denominator, and then its derivative on top, because each one of those is going to be ln eventually. So practicing this over and over again is going to make taking derivatives really a joke. As I said, it goes through the product rule, through anything really quickly. You see, this is a very nasty product rule inside the quotient rule. Each one of these was chain rule on its own, and we were just able to write the answer. So let's take a look very quickly at one of the previous chapters or sections. So let's go into a chain rule section, which was 3.7. I'm going to go into homework and pick random problem, anyone, it doesn't matter, that involves maybe product rule and chain rule together and so on. So combining rules, problems 57 through 68. Hit me. Which number? 57 through 68. It doesn't matter. Pick one. 63 it is. Wow. Nice. Dang. So 63 says, 63 from 3 point, I think it's 3.6 or something. So it says, open parenthesis, and then another open parenthesis, x plus 2, close parenthesis, open parenthesis, x squared plus 1, and then everything to the 4th power. So they definitely wanted you to use the chain rule on the outside, right, x to the 4th, and then do the product rule when you have to do the derivative of the inside. Right? But as soon as you realize that this can be written, right, this can be written as x plus 2 to the 4th times x squared plus 1 to the 4th, logarithmic differentiation makes a joke out of this. So what is the derivative? Copy the function as is. You always start there. That's always the first thing, because you will always have that 1 over y and y multiplies. And now the second part is exponent goes in front, function goes on the bottom, its derivative on top, plus, there's no denominator, both are on top, 4 x squared plus 1, and then 2x on top. And we're done. That's the derivative. We haven't done any rules, anything, any chain rules, product rules, quotient rules, nothing. It was done through logarithmic differentiation, and we are able to do it just by looking at it. If you are able to figure this out, So you have tonight and tomorrow to practice on this. Ask questions next class. I mean, I hope you see the power of this thing. But you need to go through log rules. You need to make sure that you understand how this thing works. You also see that I haven't used it directly in this form here. I distributed these fours, and then I used them separately. Now I know that I can factor out this form 4 all over, all the way in the front. But we're technically done. That's the derivative. So it's extremely powerful technique. No matter how bad the problem looks like, logarithmic differentiation is going to solve it very quickly.
So, I mean, you want us to use that method on, say, test stuff? Or?
The test is going to have exactly one problem, which will say use logarithmic differentiation to solve, and then blah. But then if this is something that you see the problem says use the product rule, you must use the product rule, because that is in a statement of the problem, and we have to have that due to the learning outcomes and so on. However, if the problem says find the tangent line blah blah blah, are you really going to embed the product rule into chain so you can do it, right? So if you learn this, right, just imagine going to Calc 2, Calc 3 differential equations. They all take derivatives, and no one will ever tell you, use the product rule, right? Because taking derivative is going to be the first step of the problem that it's going to follow for next 2-3 pages, all right? So learning this, taking derivatives down the line is nothing. For this class, yes. Product rule, quotient rule, chain rule, they're all going to understand. We'll do that. Final, sure. But that's starting Calc 2 and beyond. I hope you know this. Yes? You have to speak up. Air conditioning over here, I can't hear you. No way. If you know this very well, nothing else. You don't need anything else ever. Who honor the answer? Yeah, that's the best answer I can give you, because we also have mathematical today. Alright? So I hope that answers your question without insulting you too much.
So how would you simplify that more? You're just kick out the
4. Because now chapter 4 is going to say equal to 0. Let's find critical points. Critical points is going to be min or a max. So on. So you can technically use this for every single problem in chapter 4, because in chapter 4, no one is going to tell you use product rule and so on. It involves different things where derivative is just regularly used. Chapter 4 is applications of derivative.
So once we leave this chapter, if we know that we never brought up quotient or chain rule.
Other than the final of this class, no. But as soon as you go into calculus 2 and you go into section starts, we start Calc 2 in section 6.2. You go into section 6.5. Section 6.5 is going to have a formula that contains the derivative. Taking it this way is much faster than actually cranking any derivative there is.
So it's sort of like a faster way, like when we first learned f of x plus h of minus f of x over h. Instead of doing it that long way, we learned those rules, and then instead of those ways, we learned this one.
And that goes for mathematics at large. What mathematics is a collection of generalizations that is bringing basic calculation arithmetic on a higher level, but generalizes it more and more. See, in linear algebra, class that you can take after Calc 2, which computationally doesn't require anything past elementary algebra, computationally, but concept-wise does require even higher than Calc 2. In that class, you learn a single mathematical statement that puts all the mathematics you learned up to that point in that one statement. And then there are whole courses later on that summarize mathematics more and more and more on top of that. So it builds up. And that's the reason why, you look around and you see in this class 12 people. Because somewhere along the line, people fell off the truck because they learned one chapter for the grade to pass, and they didn't learn that concept, and that is the reason why they cannot perform in the next course. And this is what I'm telling you. Calc 2, welcome to the class. You are going to fail miserably if you don't know how to do U substitution, if you don't know those 10 or so trig identities. U substitution, which is in our class, section 5.5. We are now in chapter 3. So 5.5 is literally the last lesson of Calc 1. If you don't know that for Calc 2, you are dead in Calc 2, because every single integral problem in Calc 2 is ending with that. Even when you learn other integration techniques like integration by parts, trigonometric integrals, trigonometric substitution, the partial fraction decomposition, no matter what you learn there, it's all the ways of how to massage the problem to get in a form where you can use U sub. U sub is U sub, yeah, rather U. U substitution is backwards chain rule. Because the integrals are opposites of the differentiation. Integrals are also known as n-type derivatives. So everything that you do derivatives, you undo with integrals. What you do with integrals, you undo with derivatives. Just like e to the x ln x, kind of thing. They're inverses on each other, but they're inverses on the operator level, not on. So the most important rule for derivatives is chain rule. It's the core of implicit differentiation. It's in every single problem. The chain rule is the most important differentiation rule of all of them by far. And it's used heavily to derive this method, chain rule. It's the only one that's used to derive that rule. And by virtue that the chain rule is the most important thing for differentiation, then the backwards chain rule for integrals, which is called U substitution, is the most important method of solving integrals. And if you don't know it, you're dead in 2 chapters in Calc 2. 2 chapters are done. And that's half of the course. So that's how important that one section from Calc 1 is for Calc 2. And all of the students who miss that, because it's rushed at the end of the semester, because the professor didn't get to it, because they were moving too slow, because for whatever reason, a birthday came up on that day, or a car blew up, whatever reason it is, you don't learn that one, forget about Calc 2. And that's why for the first 2 days in Calculus 2, I just go U sub, U sub, U sub, U sub, because I know if I don't do that, by week 2, it will be half of the classroom. I have enough experience in that field. So.
I think you're going to make a point to teach that in this class?
Oh, yeah.
Definitely.
Oh, yeah. Which is the reason why every time I teach the class, the Calc 1, half of my Calc 2 are my Calc 1 students, and then 75% or 80% of Calc 3 are my Calc 1 and Calc 2 students, and so on. So Calc 3 was out of 24 students signed up for Calc 3, 6 were what I call newbies. You're all newbies for me now, because I don't know any one of you from previous classes. Like, yeah. 6 out of 24. That's because they stick around, they see that I put those specific points that you definitely must know to go to the next class. I have a student who took 6 consecutive classes. 6. 3 Calc 1, 2 Calc 1, 2, 3 differential equation. And the reason why she didn't take the 7th one is because I didn't offer it. I didn't teach linear algebra that summer. And that was it. So yeah, that's the extreme, the 6. I have a bunch of 4s. Never had the 5. See you tomorrow. Same time, same place. We do more of these. Hopefully you practice this. 2 more sections. We're done with the chapter. We should talk tomorrow about the next test date. Whatever day you pick in a week, we need to start those quizzes and stuff. Do the homework online. Enjoy this. Oh, I forgot to turn the stream off. Bye, stream.